You thought the universe was a stable machine running smoothly, completely wrong. In March 2025, data from DESI delivered a major blow to Einstein's theory. Dark energy may be weakening. That means the entire future of humanity might have just been completely reshaped. We're living inside a gigantic torture chamber, where gravity is ready to stretch you into an atomic strand of spaghetti. The order you see every night when you look up at the sky is actually just a temporary silence between the most violent collisions imaginable. If this random balance disappears, which doomsday scenario would happen first? Don't look away, because you're about to realize just how absurd the coincidence is that allows us to survive at all. Subscribe to the channel, and make sure to watch until the end of the video. Most people carry a domesticated idea of gravity. Things fall down. Planets orbit. The moon pulls on the oceans and gives us tides. The kind of physics that feels reassuring, almost gentle. Like something that belongs in the background of ordinary life, rather than at the center of the universe's most violent events. Gravity is not gentle. It is the only fundamental force in the universe with no upper limit, no saturation point, no ceiling beyond which it stops growing, and every other force in nature has at least one of those constraints. Electromagnetism can be shielded by other charges. The strong nuclear force, the one holding atomic nuclei together, operates only at distances smaller than a single proton and fades to nothing beyond that range. The weak nuclear force is, by its own name, weak, relevant only in radioactive decay and certain subatomic interactions. Gravity alone keeps scaling without limit the more mass you add. The stronger it becomes. And physics offers no rule that says it has to stop anywhere. That is what separates it from everything else. Not its familiarity, but its open-endedness. The fact that it has no off switch and no maximum. For the first 9 billion years of the universe's existence, gravity was slowly winning a war against the expansion that began at the Big Bang, the way a ball thrown upwards slows before it falls. Every galaxy pulling on every other, the collective mass of everything that exists, gradually putting the brakes on a universe that had been racing outward since the beginning. Physicists watching from Earth expected this to continue, expected that eventually the expansion would halt and reverse, that gravity would gather everything back into a single catastrophic collapse they called the Big Crunch, around 5 billion years ago. Roughly when our solar system was just beginning to coalesce from gas and dust. Something changed the calculation entirely. The universe didn't slow down, it accelerated. And the force responsible for that acceleration now makes up approximately 68% of everything in the universe, which is more than all the stars, planets, gas clouds, and dark matter combined. Scientists call it dark energy, which is a phrase that mostly functions as an admission. We have no idea what this is, but it is everywhere. It is dominant, and it is pushing. In March of 2025, a survey called the Dark Energy Spectroscopic Instrument published results from mapping 15 million galaxies across 10 billion years of cosmic history. And what those measurements suggested was that dark energy might not be a constant. It might be weakening. Slowly, subtly, but measurably. If that is true, the balance of power between gravity and dark energy, the balance that determines the ultimate fate of every structure in the universe, is not a settled question. It is an active contest whose outcome we are still watching unfold. Two possible endings live inside that uncertainty. In the first, dark energy wins completely. The expansion continues accelerating until galaxies can no longer see each other across the growing void, until stars burn out in isolation over trillions of years, until eventually the stretching of space itself becomes violent enough to tear apart atoms. And the universe ends, not with a collapse, but with a silence so complete it makes collapse look almost warm. In the second, dark energy weakens and gravity reasserts itself. The expansion slows, stops, reverses, and every galaxy, star, planet, and grain of dust in existence gets pulled back toward a single point, compressed into a density where the concepts of space and time stop having meaning. Either way, gravity is the protagonist, either as the force that lost and let entropy dissolve everything, or as the force that returned and destroyed what it had spent billions of years assembling. This is the character running through everything that follows, completely indifferent to what it builds and what it demolishes, operating by the same equations whether it's organizing a solar system or ripping matter into forms that shouldn't exist. To understand what gravity actually does when it goes unchecked, consider what it has already done at the largest observable scale: the filamentary structure of the universe, the vast cosmic web of galaxy clusters connected by bridges of dark matter and gas, separated by voids, hundreds of millions of light years across where almost nothing exists, is gravity's architecture work. Assembled over 13.8 billion years from a starting condition of near-perfect uniformity, where the density of matter varied by only about 1 part in 100,000 from one region to another. 1 part in 100,000 is an almost imperceptible difference. If you had a bathtub full of water and added 1 extra drop in the center, you would have created a density variation larger than the ones gravity had to work with at the beginning of the universe. And from those nearly imperceptible differences, gravity built everything, every star, every galaxy, every cluster, every filament, every structure visible in the deepest images the Hubble and James Webb Space Telescopes have ever captured. The capacity for creation implied by that fact is staggering, and it is the exact same capacity, operating at smaller scales and higher densities, that produces the destructive extremes we will spend the rest of tonight exploring. Because gravity's creative process and its destructive process are not different mechanisms. They are the same mechanism operating across different ranges of the same parameter space. The force assembling a galaxy over billions of years and the force tearing a star apart in hours are expressing the same mathematical relationship between mass, distance, and acceleration. Scale changes the outcome, but the equation is identical. And when gravity gets enough material to compress, when a dying star finally runs out of the nuclear pressure that was holding it open from the inside, what happens to matter itself is something that rewrites your understanding of what matter is allowed to be. Every object you have ever touched in your life, every wall, every piece of food, every other person, is mostly empty space. The nucleus of an atom is so small relative to the electron cloud surrounding it that if you scaled an atom up to the size of a football stadium, the nucleus would be a grain of sand at the center, and the electrons would be specks of dust orbiting somewhere near the outermost seats, with nothing but vacuum in between. All of the matter you interact with, everything you think of as solid, is essentially a pattern of electric forces maintaining the illusion of solidity across enormous proportions of empty space. Inside a neutron star, that empty space is gone. When a massive star exhausts its nuclear fuel after billions of years of burning, the outward pressure of fusion, the force that was holding the star's own gravity at bay, disappears in a fraction of a second, and gravity, which had been waiting, collapses the entire stellar core in less time than it takes your heart to beat once. The implosion is so violent, so total, that the electrons which were orbiting atomic nuclei get forced directly into those nuclei, merging with protons to form neutrons. And the result is an object that is, in essence, a single enormous atomic nucleus, the size of a city. Consider what that means in practical terms. an object with a diameter of approximately 20 kilometers, smaller than many urban metropolitan areas, containing more mass than the entire Sun, which is itself large enough to swallow 1,300,000 Earths. A single teaspoon of material from inside a neutron star would weigh approximately 1 billion tons on Earth, which is roughly equivalent to the combined mass of every human being who has ever lived across all of recorded history, compressed into an object you could hold between two fingers. The density is 100 trillion times greater than anything you encounter on the surface of this planet, a number that isn't really comprehensible as a number, but becomes slightly more concrete when you consider that the air you are breathing right now is, by comparison, practically indistinguishable from a perfect vacuum. Atomic structure, the fundamental architecture of all matter as we experience it, ceases to exist inside these objects, replaced by something that physics can describe mathematically, but that has no analog in any material a human being has ever held or built or imagined building. The formation of a neutron star from a collapsing stellar core happens in approximately 1 second. In 1 second, an object with a mass greater than the Sun transitions from a hot, compressed iron core, already the endpoint of a star's nuclear burning sequence, the ash left after all lighter elements have been fused, to a sphere of pure nuclear matter 20 kilometers across, releasing more energy in that 1 second than the Sun will release across its entire 10 billion year lifetime. The energy release takes the form of neutrinos, ghostly particles that interact so weakly with normal matter that they pass through the entire Earth as if it weren't there, and a single core collapse supernova releases more neutrinos than the Sun produces across 10 billion years of fusion. In 1 second, streaming outward through the collapsing stellar envelope and carrying 99% of the explosion's total energy. The visible supernova that astronomers observe, the brilliant flash outshining an entire galaxy for weeks, is the remaining 1%. What's left at the center is the neutron star, the most extreme state of matter that remains observable, that still occupies a defined region of space and has a surface you could theoretically describe, before the final endpoint of gravitational collapse produces something from which no information escapes at all. And inside the crust of these objects, something even stranger is happening, something that required decades of supercomputer modeling to even partially understand, and that was given a name borrowed from a dinner table, about 1 kilometer beneath the surface of a neutron star's crust, at pressures so extreme they cannot be recreated in any laboratory on Earth or anywhere near Earth. Atomic nuclei stop behaving like discrete spherical objects and begin merging, stretching, and reorganizing themselves into extended structures that have no equivalent in ordinary chemistry or materials science. The shapes they form, which physicists have mapped through simulations requiring the equivalent of 2 million hours of computer processing time, roughly 250 years of continuous calculation on a standard laptop, are, at their most basic level, the shapes of pasta. In the outer layers of this region, nuclei cluster into roughly spherical blobs that physicists call gnocchi. Deeper in, under greater pressure, those blobs elongate into long cylindrical tubes, spaghetti. Deeper still, the tubes flatten into broad sheets, lasagna. And beyond that, as the pressure approaches the inner boundary of the crust, the geometry inverts. Instead of nuclear matter surrounded by empty space, the empty space becomes the tubes and channels running through a solid matrix of nuclear material, forming what are called anti-spaghetti and anti-lasagna structures, a topological reversal that has no intuitive equivalent in the world of food from which these names were borrowed. The collective term for all of these phases is nuclear pasta, and the question physicists spent years trying to answer was how strong it actually is, whether the material properties of these structures had any measurable consequence for the neutron stars containing them. The answer, published after those 2 million hours of computation, was that nuclear pasta is the strongest material known to science anywhere in the observable universe, requiring a force approximately 10 billion times greater than the force needed to break steel in order to fracture it. For comparison, the strongest materials humans have ever manufactured, things like graphene and carbon nanotube composites, which are themselves extraordinary by any earthly standard, fail at forces that are not even in the same conceptual neighborhood. 10 billion times stronger than steel is a ratio for which ordinary language does not have adequate vocabulary, because human engineering has never encountered a problem that required material strength anywhere near that order of magnitude. And the reason this matters beyond pure scientific curiosity is that nuclear pasta likely influences how neutron stars wobble, spin, and produce gravitational waves, the ripples in spacetime that LIGO detects from Earth, and the tiny surface irregularities created by the pasta structure. Mountains on neutron stars that stand perhaps a few centimeters tall are generating gravitational wave signals that sensitive enough detectors might soon read directly. A centimeter-tall mountain on a neutron star, producing detectable ripples in the fabric of spacetime, which is to say, the most exotic material in the universe is announcing its existence through the most exotic phenomenon in physics. And we are close to being able to listen. There is another dimension to what nuclear pasta represents that goes beyond its mechanical strength, which is what it tells us about the range of states that matter is capable of occupying under different conditions. On Earth, at the pressures and temperatures accessible to human technology, matter organizes itself into phases: solid, liquid, gas, plasma, and transitions between those phases at well-defined thresholds that chemists and physicists have spent centuries mapping with precision. Inside a neutron star's crust, those phase boundaries continue to exist, but they describe transitions between states of nuclear matter that have no names in ordinary chemistry, because the conditions producing them cannot exist at the surface of any planet and cannot be recreated in any facility humans have built or could realistically build. Nuclear pasta represents a class of phase transitions, from gnocchi to spaghetti to lasagna to their topological inverses, that occur inside a region approximately 1 kilometer thick. As pressure increases over a range that spans from roughly the nuclear saturation density at the top to several times that density at the bottom. And the phases cycle through geometries that are described not by the language of solid-state physics, but by the mathematics of minimal surfaces and topology. It is matter organized by forces and at scales that have no terrestrial equivalent, doing things that are physically permitted but practically impossible to observe directly. And the only window into its behavior is through the gravitational wave signals produced by neutron stars wobbling on millisecond timescales as they rotate. The wave patterns encoding information about the internal structure in the same way that seismic waves from earthquakes encode information about Earth's internal layers. Gravitational wave astronomy, which has existed as an observational field only since the first LIGO detection in 2015, is currently the only tool that can probe nuclear pasta from Earth, and it is a tool that is still developing its sensitivity, still adding detectors, still expanding its reach. In the same decade that physicists named nuclear pasta, mapped its phases, and calculated its strength, the field of gravitational wave detection went from 0 confirmed detections to a catalogue of hundreds of merger events. And the intersection of those two developments means that the question of what lives inside neutron stars is moving from theoretical inference toward observational constraint. The hardest material in the universe might, within the lifetime of instruments currently under construction, be measurably detected, not by sending anything there, but by listening to the gravitational hum of its existence from thousands of light years away. But nuclear pasta, extraordinary as it is, represents only one of the ways matter transforms under gravitational extremity. because some neutron stars carry an additional property that makes their interior structure almost secondary to the field they project into the space around them. A neutron star with a magnetic field strong enough to restructure the behavior of atoms at a distance is called a magnetar, and there are approximately 30 of them known to exist within the Milky Way. 30 objects, scattered across a galaxy containing 400 billion stars, each one representing a category of physical phenomenon so extreme that it requires new frameworks to describe. The magnetic field of Earth, the field that orients compasses, deflects solar wind, and protects the biosphere from charged particle radiation, measures roughly half a Gauss at the surface. The magnetic field of the strongest electromagnet humans have ever constructed in a laboratory setting measures approximately 45 Tesla, or 450,000 Gauss. The magnetic field of a magnetar measures, at its surface, somewhere between 10 to the power of 14 and 10 to the power of 15 Gauss, which is between 100 billion and 1 trillion times stronger than our most powerful engineered magnet, and approximately 1 quadrillion times stronger than the field protecting the planet you are sitting on. At that field strength, quantum electrodynamics, the physics governing how light and matter interact, begins to produce effects that simply do not occur anywhere else in the observable universe. The electron clouds around atoms, which, in ordinary matter, form roughly spherical shells, get squeezed along the field lines into elongated cylinders, approximately 200 times narrower than their normal configuration, meaning a hydrogen atom near a magnetar surface is not a sphere but a tube, a fundamentally different shape with fundamentally different chemistry. And the chemistry of every molecule in existence depends on the electron shell geometry that magnetar proximity would destroy. The practical consequence is that within approximately 3,000 kilometers of a magnetar, a distance smaller than the diameter of the Moon, the electromagnetic forces holding molecular bonds together would be overwhelmed by the external field, and the atoms in a human body would be deformed into shapes incompatible with the chemical reactions that constitute life, with no violence, no explosion, no dramatic event, just the quiet cessation of every biological process simultaneously. From a distance equal to roughly half the separation between Earth and the Moon, about 150,000 kilometers, the field would be strong enough to erase every magnetic storage device on Earth simultaneously, which, in practical terms, means every credit card, every hard drive, every MRI machine, every piece of magnetically stored data in human civilization, wiped in the same instant. On December 27, 2004, a magnetar designated SGR 1806-20, located 50,000 light-years away, which means on the far side of the Milky Way, approximately halfway across the galaxy, released a burst of energy in a fraction of a second that was measurable from Earth. In approximately 1/10 of a second, that object emitted more energy than the Sun produces across 150,000 years of continuous fusion. The ionosphere of Earth, the electrically charged upper layer of the atmosphere that radio waves bounce off of, visibly compressed on the side facing the magnetar. Several satellites experienced temporary blindness from the radiation, and the event registered on instruments designed to detect gamma-ray bursts from throughout the observable universe. This happened from 50,000 light-years away, a distance so large that the energy had been traveling since before anatomically modern humans existed on this planet, since before the last Neanderthals walked the Earth, since before the cave paintings at Lascaux were drawn, and the recorded event was, by the standards of known magnetar physics, relatively moderate, smaller than the most energetic burst class, detectable but not catastrophic, a magnetar at 10 light-years distance, about twice as far as the nearest star system to our own, would produce a gamma-ray burst strong enough to strip the ozone layer, ending the atmospheric protection that shields all land life from ultraviolet radiation, with consequences that would propagate through the food chain over years and decades. There are no magnetars that close currently, which is the appropriate qualifier for a galaxy that contains 30 known magnetars, likely far more unknown ones, and objects moving through it at velocities that make long-term neighborhood stability a matter of probability rather than guarantee. In 2025, NASA confirmed that a magnetar designated SGR 0501 +4516 has been moving through the Milky Way without any traceable origin point. Its trajectory doesn't lead back to any known stellar nursery, any supernova remnant, any region where it might plausibly have formed, suggesting either that it formed through a mechanism not yet understood, or that it was ejected from its formation site with such velocity that the evidence of its origin has dispersed beyond detection. A magnetar of unknown origin, moving through the galaxy at an untracked velocity, with a field strong enough to restructure atomic physics at range. This is the category of object that makes the solar system's current stability feel less like a permanent condition and more like a streak of good fortune that has continued for 4.5 billion years without interruption. The violence a magnetar projects outward through its field represents one category of extreme physics: energy and force radiating away from an object, reaching into space and restructuring what it touches. The other category runs in the opposite direction, the violence of gravity pulling inward, concentrating, accelerating, dragging matter not just toward an object but through a transformation from which it emerges in a form no longer recognizable as what it was. The term spaghettification appears in peer-reviewed astrophysics literature, is used in formal scientific communications from NASA and ESA, and describes a real physical process that is currently happening to real astronomical objects in real time, right now, in galaxies scattered across the observable universe. When an object approaches a sufficiently dense gravitational source, a neutron star, a stellar mass, black hole, a supermassive black hole at the center of a galaxy, the side of that object closest to the gravitational source experiences a stronger pull than the side facing away, because gravity weakens with distance, and even across the length of a body. That gradient becomes significant. For a human body approaching a stellar mass black hole, the difference in gravitational force between your feet and your head would be sufficient to stretch you vertically while simultaneously compressing you horizontally, the feet accelerating toward the singularity faster than the head can follow, the sides pushed inward by tidal compression, the whole body elongating into a narrowing stream of matter that spirals inward along a path that is no longer describable as a trajectory in any ordinary sense. Stars undergo the same process at larger scales. A star wandering too close to a black hole gets stretched into a curved ribbon of superheated plasma, and roughly half of that material wraps around the black hole and falls inward, forming what is called an accretion disk, a churning, luminous structure radiating more energy per unit mass than almost any other process in astrophysics, while the other half gets flung outward at velocities approaching 10,000 kilometers per second. 10,000 kilometers per second is approximately 3.5% of the speed of light, which means material from a torn-apart star is being ejected fast enough to cross the entire diameter of the solar system in about 15 hours. In May of 2025, NASA announced the discovery of a supermassive black hole that was not where supermassive black holes are supposed to be, not at the center of its host galaxy, but 2,600 light-years from that center, drifting through the galaxy's outer regions, an exile from the gravitational anchor that should have held it in place, and the way it announced itself was by catching a star, stretching it, consuming it in the event designated AT 2024 TVD, a tidal disruption event that lit up across multiple wavelengths and confirmed the object's existence and position through the flash of its meal. In July of 2025, the James Webb Space Telescope observed 4 additional tidal disruption events occurring inside dust-enshrouded galaxies. Galaxies where the dust content would have made the events completely invisible to any instrument operating at optical wavelengths, meaning that the true rate of stellar destruction by black holes across the universe has likely been significantly underestimated, because the detectors we relied on for decades couldn't see through the curtain. And in December of 2025, astronomers published observations of a black hole actively twisting the space-time around it in real time. The disk of material feeding the black hole and the jet of energy it was launching, both oscillating with a 20-day period in a pattern called lens-Thirring precession. The first direct observational confirmation of a prediction Einstein made more than a century ago about what a rotating mass does to the geometry of space around it. There is also a reversal worth sitting with the most destructive form of spaghettification, the complete tidal destruction of an infalling object is actually less likely to occur at the event horizon of the largest black holes than at smaller ones. A black hole with a mass 10 billion times that of the Sun has an event horizon so large, and the tidal gradient across that horizon so gradual, that an object passing through it would experience relatively mild tidal forces, mild enough that a person crossing the event horizon of a supermassive black hole might feel nothing unusual, might have no sensation of crossing any boundary at all, and would only discover the irrevocability of what just happened as they continued inward, and the tidal forces eventually grew strong enough to matter. The boundary that ends everything offers no warning at the moment it is crossed, which raises a question worth sitting with. If a person were falling into a supermassive black hole and crossed the event horizon without feeling anything unusual, how would they know? The answer, according to general relativity, is that they would know only in retrospect, not by any sensation at the boundary, but by the fact that any direction they subsequently tried to move, including outward, would lead them closer to the singularity rather than farther from it. Inside the event horizon of a black hole, the dimension we experience as time and the dimension we experience as space toward the center exchange roles. Moving toward the singularity is not a choice, but a consequence of existing in time. The same way that aging is not a choice for anything in the external universe. You cannot stop moving toward the singularity inside a black hole any more than you can stop aging outside one, because both are expressions of the same physical necessity, the forward direction of time. This is not metaphor. It is a literal description of the geometry of space-time inside an event horizon. The same geometry that general relativity has been confirmed to describe correctly by every precision test conducted since Einstein formulated it. The singularity at the end of that inward fall is the point at which the theory predicts density becomes infinite, curvature becomes infinite, and the mathematical framework that describes everything else in the universe ceases to produce finite, meaningful outputs, which is most likely an indication that quantum mechanics intervenes at that scale in ways the current formulation of general relativity cannot account for, rather than that infinities literally exist in nature. What actually happens at that point is the central unsolved problem in theoretical physics, the meeting place of general relativity and quantum mechanics that neither theory can describe on its own, the edge of current human understanding about what the universe is made of and how it behaves under the most extreme conditions that can exist, which is where the other side of the black hole equation becomes relevant. The possibility that the ending described by classical general relativity is not actually an ending, but a transition point to something the mathematics of a combined quantum gravity theory is just beginning to describe. Einstein's field equations, the mathematics that describes how mass curves spacetime, are time-symmetric. Run them forward, and they describe a black hole, a region of spacetime where the curvature is so extreme that all possible paths through space and time lead inward. where escape velocity exceeds the speed of light and therefore nothing that enters can exit. Run them backward and they describe something that has never been directly observed, a region where all possible paths lead outward, where matter and energy can only emerge and never enter. A source without a drain. A white hole. The mathematics permits both objects with equal formal validity. The physics community has debated for decades whether white holes represent a genuine feature of the universe or merely a mathematical artifact, a solution to an equation that describes something real, in the same way that a square root can produce both a positive and a negative answer, while only one of them corresponds to an actual measurement. In 2025, a paper in Physical Review Letters reignited that debate by proposing that the singularity at the center of a black hole, the point where density becomes infinite and general relativity breaks down, is not actually a terminus, but a transition, a moment where quantum gravitational effects halt the compression before it reaches infinity and cause the accumulated matter to begin expanding outward, transforming the black hole into a white hole through a process called a quantum bounce. The framework, drawn from loop quantum gravity, but carries a consequence that is almost impossible to hold in mind comfortably from inside the collapsing system. The bounce happens in a microsecond, from outside, from the perspective of any observer in the external universe. The process takes longer than the current age of the universe to complete, because of the way extreme gravity distorts the flow of time near the event horizon, stretching a microsecond of internal time into billions of years of external time. This is not a bug in the theory. It is a direct consequence of the same time dilation that GPS satellites have to correct for, the same effect that makes clocks run slower in stronger gravitational fields. Extrapolated to its extreme limit at the boundary of a black hole where the time dilation factor approaches infinity. The information problem in black hole physics. The long-standing question of what happens to the quantum information describing every particle that falls into a black hole. Given that quantum mechanics requires information to be conserved, and classical black hole theory says it's destroyed, finds a potential resolution in the white hole bounce scenario. Because if the black hole eventually transforms and releases its contents, the information was never truly lost, just stored in a form inaccessible from the outside during the intervening period. Stephen Hawking spent the latter part of his career working on this problem and revised his position multiple times, ultimately suggesting that information escapes in subtle correlations within the Hawking radiation that slowly evaporates the black hole over astronomical timescales. But the white hole bounce model offers a different resolution, one in which the information doesn't leak out gradually but waits, compressed, for the full transformation to complete. Two different proposed mechanisms for preserving the universe's accounting of itself, operating over timescales that make the current age of the universe look like a rounding error. The information swallowed by a black hole at the moment of a stellar death could, in this model, still be inside, waiting, compressed, suspended in a kind of gravitational slow motion, and will eventually emerge as the black hole completes its transformation, releasing everything it consumed across a timescale that makes billions of years sound brief. This would mean that white holes are not theoretical edge cases, but real objects, distributed throughout the universe. Each one a black hole in its final phase. And because the timescales involved are so extreme, we would have no way of distinguishing a young white hole from an ordinary energetic astrophysical event. The universe might be full of them, releasing their contents in the form of phenomena we've already catalogued under different names. And the only reason we haven't recognized them is that the connection between the black hole that formed and the white hole releasing its contents spans a gap in time longer than anything human cognition can intuitively process. Also, in 2025, the James Webb Space Telescope detected a black hole existing entirely alone in the early universe, 50 million times the mass of the Sun. present when the universe was only 1 billion years old, with no host galaxy around it. No stellar population to have produced it through the standard sequence of stellar evolution and collapse. A black hole that should not exist by any currently accepted model of structure formation. Sitting in the early universe without explanation. Challenging every framework physicists have built for understanding how these objects form and grow. Quantum magazine described it as paradigm shifting, which in scientific communication is approximately the equivalent of admitting that a foundational assumption has been invalidated and the reconstruction has not yet begun. What the black hole and white hole together represent is a kind of cosmic accounting, matter that flows in one direction for an inconceivable period, then flows back the other way, neither truly created nor destroyed, only transformed, held in the longest pause that physics permits before the equation runs in reverse. The same mathematics that describes the most total consumption in nature also describes total release, and the universe is apparently patient enough to let both sides of that equation play out in full. The Milky Way and the Andromeda Galaxy are moving toward each other at approximately 110 kilometers per second, which sounds like a collision course until you consider that the distance between them is 2.5 million light-years. A gap so large that even at that velocity, the closing time is measured in billions of years. And as of June 2025, we are no longer certain the collision will happen at all. A study published in Nature Astronomy, using data from both the Hubble Space Telescope and the Gaia mission, Gaia being a spacecraft that has measured the precise positions and velocities of nearly 2 billion stars with an accuracy equivalent to detecting the width of a human hair from 3,000 kilometers away, ran 100,000 simulations of the future interaction between the Milky Way and Andromeda, varying 22 different parameters, representing uncertainties in the current measurements. The result was approximately 50-50 roughly equal probability that the two galaxies merge in several billion years, and roughly equal probability that they do not, that they undergo a close pass and then separate, continuing as distinct structures. The collision that astrophysics textbooks had presented as inevitable revealed instead as a coin flip. The reason the outcome is so uncertain comes down, surprisingly, to a third galaxy, the Large Magellanic Cloud, a satellite galaxy of the Milky Way, with a mass approximately 15% of its host, whose orbital trajectory is nearly perpendicular to the direction Andromeda is approaching from, and whose gravitational influence has been gradually pulling the Milky Way sideways, off the direct line toward Andromeda. The Large Magellanic Cloud was always there, always exerting its gravitational influence. It just wasn't measured with sufficient precision to include in the collision calculation in a way that changed the answer. Until the Gaia mission produced its catalogue of nearly 2 billion stellar positions and velocities with an accuracy equivalent to detecting the width of a human hair from 3,000 kilometers away. That instrument, combined with Hubble's long baseline observations, gave the team enough data to constrain the Milky Way's transverse velocity, its sideways motion relative to Andromeda, accurately enough to see that the Large Magellanic Cloud's influence has already pulled the Milky Way off the direct collision course, and that whether the perturbation is sufficient to avoid merger entirely depends on parameters still being refined. The update is not just a correction to a specific prediction about a specific event billions of years away. It is a demonstration that the most confident statements in astrophysics are confidence intervals, not certainties, and that the intervals shrink only as instruments improve. One of the co-authors of the study wrote that claims about the imminent demise of our galaxy appear to have been significantly overstated, which is a restrained way of saying that decades of confident projections were based on incomplete data, and the full picture is considerably more ambiguous. What makes this worth sitting with is not just the revision of a specific prediction, but what it illustrates about the limits of certainty at cosmic scales, that even events we had calculated down to a specific time frame, Events we had visualized in computer simulations and depicted in planetarium shows can be reclassified as uncertain when better measurements arrive. But even if the collision never happens in the full merger sense, even if the two galaxies pass each other like ships in a cosmic night, the gravitational interaction during that closest approach would be sufficient to reshape both structures profoundly, tidal forces stretching and distorting the disk of the Milky Way, star-forming regions compressed and triggered into bursts of stellar birth, the positions and velocities of billions of stars permanently altered by the passage. And the specific concern for any planetary system in the Milky Way is not direct stellar impact. The stars in both galaxies are so widely separated relative to their individual sizes that the probability of any two stars actually striking each other during even a full merger is vanishingly small, comparable to firing two shotgun blasts at each other from opposite ends of a continent and expecting the pellets to collide in mid-air. The danger is orbital disruption, gravitational perturbations that change the trajectory of a solar system without touching it, that alter the relationship between a star and its planets gradually over millions of years, that could move a habitable planet just far enough from its star to begin a slow transition toward uninhabitable, or that could eject it from the stellar system entirely, setting it adrift in the space between galaxies where no starlight reaches. There is approximately a 12% probability that the Sun, during even a relatively close galactic interaction, would be gravitationally displaced into a completely different region of whatever galaxy forms from the encounter, still intact, still fusing hydrogen, but surrounded by a different stellar neighborhood, in a different part of a different structure, with no memory in its motion of where it began. 12% is the kind of number that sounds small until you consider what it represents. 1 in 8 chance of the entire solar system becoming something we don't have a word for yet. Not homeless. Exactly. But relocated without consent into a universe it doesn't recognize. Of all the ways the stability of the solar system can be disrupted, the most quietly unsettling is probably the least cinematic. Not a collision, not a dramatic energy release, but a star or black hole traveling through the galaxy on an independent trajectory, intersecting the solar system's space, not by targeting it, but by coincidence of orbital dynamics, close enough to exert measurable gravitational influence, without ever becoming visible to the naked eye as anything more than an unusual point of light. At the outermost edge of the solar system, at distances ranging from 2,000 to 100,000 astronomical units from the Sun, 1 astronomical unit being the Earth-Sun distance, meaning the outer edge of this region sits roughly 1.5 light-years away. There exists a vast, poorly mapped reservoir of icy objects called the Oort cloud, a spherical shell containing somewhere between 100 billion and several trillion comets and proto-cometary bodies that have been in stable, slow orbits for billions of years, held loosely in place by the Sun's gravity at a distance where even the slightest additional gravitational perturbation can alter their trajectories substantially. The Oort cloud is, in effect, the solar system's most sensitive gravitational instrument, a structure so large and so loosely bound that a star passing through the outer edges leaves a measurable signature in the form of comets, whose orbits get redirected inward, toward the inner solar system, years to millions of years after the star has already moved on. The star designated Schultz's star passed through the outer Oort cloud approximately 70,000 years ago, when anatomically modern humans were already present on Earth, when the ancestors of every person alive today were hunting and painting and navigating by the stars of a sky that included, for a brief period, this interloper drifting past at close range. The comets it disturbed are still moving. Some of them, redirected by Schultz's star 70 millennia ago, are currently traveling through the outer solar system, on trajectories that will bring them into the inner solar system in the coming millions of years. and there is no way to know which specific objects were nudged by that passage and which were already on their current paths before it happened. A more precisely calculable encounter is already on the calendar. The star Gliese 710, currently 62 light-years away. A dim orange dwarf, with about 60% the mass of the Sun, is moving directly toward the solar system and will pass through the Oort cloud in approximately 1.29 million years. Updated calculations published in 2025 revised the expected closest approach distance to be significantly closer and the timing to be approximately 70,000 years earlier than previous estimates, and determined that Gliese 710 will penetrate deeply enough into the Oort cloud to gravitationally perturb a substantial fraction of the objects in that region. At closest approach, Gliese 710 will be bright enough to see with the naked eye, visible as a point of light in the night sky, comparable in brightness to Jupiter, not dramatic enough for most observers to recognize as unusual, but gravitationally active enough to have already begun distorting the outer Oort cloud by the time it reaches maximum brightness. The aftermath will not be immediate. The comets redirected toward the inner solar system by Gliese 710's passage will arrive over a period of 3 to 4 million years following the encounter, a prolonged, diffuse bombardment rather than a single event, spread across a time frame longer than the entire existence of the genus Homo. Astronomers estimate that during the peak period of this enhanced influx, Earth could experience approximately 10 bright, naked-eye comets per year, compared to the current rate of roughly one every several years, and that this statistical enhancement of impact probability, sustained across millions of years, would cumulatively represent a significant elevation in large body collision risk. Comets, for reasons of composition and velocity, deliver approximately 10 times the destructive energy of asteroids of equivalent mass. They arrive faster. They are less likely to have been detected in advance, and their volatile-rich interiors generate atmospheric effects that rocky impactors do not. What Gliese 710 represents is a category of threat that has no analogue in human experience, not a danger that approaches and can be tracked and assessed, but a trigger mechanism that sets other things in motion across timescales that exceed the entire recorded history of civilization by factors of thousands. The star itself poses no direct hazard. What it leaves behind, the perturbation pattern it imprints on 100 trillion loosely bound objects that have been sitting quietly for billions of years, is the actual consequence. And that consequence will play out long after the star has continued on its way and is indistinguishable from any other dim point in a different part of the sky. The galaxy contains an estimated 40,000 rogue stellar encounters that have disturbed the Oort cloud over the 4.5 billion year history of the solar system, each one adding its perturbation signature to a cumulative statistical enhancement of inbound comet flux that has, over geological time, contributed to the impact record we can read in the craters of the Moon and the mass extinction events preserved in Earth's geological strata. The stability we experience, the long periods between large impacts that have allowed complex life to develop and persist, is not the absence of threat, but the spacing between them. The gaps between perturbation events where the perturbed material hasn't yet arrived, and somewhere in the outer solar system, moving inward at a velocity that would be invisible without specialized tracking systems. There are objects already on their way from disturbances that happened thousands or millions of years ago, working their way through the gravitational web of the outer planets, unannounced and unobserved until they cross the detection threshold of whatever instruments are operating when they arrive. What this means is that the most consequential cosmic events in Earth's future may already be in motion, not approaching from outside the solar system, but already inside it, already redirected, already committed to a trajectory whose endpoint is a matter of geometry and time rather than probability. The universe doesn't announce its intentions. It sets things in motion, and the setting in motion and the arrival are separated by intervals that dwarf the entire history of human civilization, which means that from the inside of any given era, the situation appears stable, because the consequences of the last perturbation haven't manifested yet, and the next perturbation hasn't happened yet, and the window between them is wide enough to mistake for permanence. This is, in a way, the defining characteristic of cosmic scale threats. They are not fast enough to be dramatic and not slow enough to be ignorable, operating instead across timescales that fall precisely into the gap between human intuition and geological patience. Too long to watch unfold, too consequential to dismiss, and too certain to dispute once the orbital mechanics are calculated with sufficient precision. The Gliese 710 encounter in 1.29 million years is not a prediction that could be wrong by an order of magnitude. It is the kind of calculation that improves with better measurements, rather than being overturned by them. Because the physics governing stellar trajectories at galactic scales is well understood, the uncertainties are in the initial conditions rather than the governing equations, and the range of outcomes all involve meaningful disturbance to the outer solar system. Something will happen. The timing and severity can be refined. The category of event cannot be avoided. And beyond Gliese 710, the galaxy contains thousands of additional encounters spread across billions of years of future history, each one leaving its perturbation signature in the Oort cloud, each one redirecting a statistical sample of objects toward the inner solar system, each one contributing to the cumulative bombardment record that future geologists, if they exist, will read in the craters and extinction events of a planet that survived through a combination of favorable positioning and the vast, protective distances that make the solar system feel peaceful from inside. The rogue object category is ultimately about the same thing the entire night has been about. The forces that make the universe interesting are the same forces that make it dangerous. And the stability we experience is not the default state of the cosmos, but the temporary outcome of conditions that could, given different initial circumstances or the wrong encounter at the wrong time, have produced something entirely different. Every star system in the galaxy is navigating the same statistical landscape, surrounded by the same rogue objects, exposed to the same perturbation events, situated within the same evolving galactic structure, and the ones that have managed to maintain habitable planets across billions of years have simply been on the fortunate side of those probabilities for long enough for complexity to take root. That is the full picture of what cosmic order actually is, not a guarantee, not a permanent fixture, but a sustained improbability, maintained by the ongoing absence of the things that would end it, for a duration that has so far been sufficient to produce observers capable of appreciating how unlikely it is. Everything covered tonight. Nuclear pasta that defies terrestrial materials science by 10 billion times. Magnetars that restructure atomic geometry from halfway across the galaxy. Black holes that spaghettify stars into spiraling plasma ribbons. The uncertain future of the galactic neighborhood. The slow comet delivery system that rogue stars leave behind them as they pass. All of it is happening right now, simultaneously, in different parts of the observable universe. The solar system is not an island of stability surrounded by a peaceful cosmos. It is a temporary equilibrium within an active, violent, perpetually restructuring universe, held in its current configuration by a specific combination of distances, masses, velocities, and relative positions that has been roughly consistent for 4.5 billion years, and will remain roughly consistent for perhaps another 5 billion years, which is the timescale on which the Sun begins its own transformation into a red giant, expanding to roughly 250 times its current diameter, engulfing the orbits of Mercury, Venus, and possibly Earth, before eventually shedding its outer layers and collapsing into a white dwarf roughly the size of Earth, but containing the mass of the current Sun. That event, the death of the Sun, will occur before any of the galaxy-scale interactions discussed tonight reach their conclusions. Before Gliese 710's Oort cloud perturbation delivers its full comet complement. Before the question of Milky Way and Andromeda's future relationship is resolved. Before the white holes formed from currently existing black holes have completed their transformation, the Sun's death is the nearest catastrophic disruption on the calendar, and it is 5 billion years away. A span of time so long that the modern human species, in its current form, has existed for only about 4/10,000ths of it. The precision of the conditions required to produce what we consider ordinary existence is striking in retrospect. Earth occupies what planetary scientists call the habitable zone around the Sun, the band of orbital distances within which liquid water can exist on a planetary surface, and the width of that zone is narrow enough that a 5% shift in Earth's orbital distance would push surface temperatures permanently above the boiling point of water or permanently below the freezing point, ending the liquid water cycle that all known life depends on. The orbital distance that produces this equilibrium is maintained by a balance of initial conditions set 4.5 billion years ago and preserved by the gravitational architecture of the solar system. Jupiter's mass acting as a partial deflector for incoming debris, the Moon's mass stabilizing Earth's axial tilt, the current absence of any sufficiently massive nearby stellar perturber, none of which was designed, all of which is coincidental, and any one of which could be disrupted by events originating far outside the solar system and arriving without announcement. In March of 2025, the DESI survey's revised measurements of dark energy introduced a new layer of uncertainty into cosmological projections at the largest scale. If dark energy is weakening rather than constant, the standard model of cosmic evolution, which had given astrophysicists a relatively confident picture of the universe's future across trillions of years, needs revision in ways that are not yet fully worked out. The simplest version of what cosmologists now face is that the two most important forces shaping the large-scale structure and ultimate fate of the universe, gravity and dark energy, are both less thoroughly understood than the field had assumed a decade ago, and the measurements that were supposed to settle their properties have instead opened new questions. This does not mean physics is broken. The existing frameworks describe everything we can measure with extraordinary precision, and the revisions being made are refinements of deep parameters rather than abandonments of core principles. What it means is that the universe is more complex at its foundations than the models built to describe it, and that complexity means the future remains genuinely open in ways that a more confident period of cosmology might have declared closed. The order we observe in the motion of planets, in the long-term stability of stellar systems, in the gradual evolution of galaxies, is real, but it is not permanent, and it is not guaranteed. It is the outcome of specific conditions operating within specific ranges for a specific duration, maintained by a balance of forces that are themselves subject to dynamics operating at scales and timescales that make human civilization appear instantaneous. Every structure in the universe that we would recognize as stable, a star, a solar system, a galaxy, a cluster of galaxies, is a temporary configuration of matter and energy in a universe that began in a state of near-perfect uniformity and has been evolving, through the operation of these same forces, towards states of increasing complexity and eventually increasing dissolution. The nuclear pasta inside a neutron star is the hardest material in the universe because the conditions creating it are the most extreme known to physics. And those extreme conditions are themselves the product of stellar death, the ending of a system that had existed in the kind of equilibrium we consider normal. The Magnetar projecting its field across half a galaxy is a neutron star whose rotational energy and magnetic field haven't yet decayed to the point of quiescence, a temporary phase in the long-term evolution of what was once a stable, ordinary massive star. The black hole stretching a passing star into a spiral of plasma is the endpoint of that same stellar evolution. The final collapse of a core that spent millions of years in a balance between outward fusion pressure and inward gravitational pull, and whose moment of imbalance produced the most gravitationally extreme object matter can become while remaining localized. The question of whether the Milky Way and Andromeda will merge, now answered as uncertain rather than inevitable, illustrates something important about the nature of cosmic stability. Even the largest structural units in the observable universe are subject to dynamics that play out over timescales, long enough to look like permanence from inside them. From within a galaxy, the galaxy feels fixed. From the perspective of the universe's full timeline, it is a temporary concentration of matter in a slow dance with neighboring concentrations, influenced by satellites and dark matter halos and large-scale cosmic structure in ways that make its long-term trajectory impossible to predict with confidence. The rogue star passing through the Oort cloud encapsulates something fundamental about the nature of threats operating at cosmic scale. The most consequential disruptions are not the ones that arrive with visible force and immediate impact, but the ones that pass through without appearing dangerous and leave their consequences behind them in the form of altered trajectories, redirected objects, and changed probabilities that take millions of years to fully manifest. We are, at this specific moment in cosmological time, sitting inside a particularly stable period of a galaxy that has not had a major merger event in approximately 10 billion years, orbiting a star that has approximately 5 billion years of main sequence life remaining, on a planet that has maintained liquid water at its surface for 4 billion years, in a solar system whose current architecture deflects the majority of potentially hazardous debris before it reaches the inner planets. That stability is real, and it is also, by the standards of the universe's full timeline, a brief episode in a much longer story, one in which the forces described tonight are operating continuously, restructuring matter into forms that would be unrecognizable to any observer anchored to ordinary experience, at scales and timescales that make the span of human history appear as a single point on a line, extending from the first moment of the universe to its last. The fragility of order is not a cause for alarm. It is a cause for orientation. Every object, every structure, every stable arrangement of matter in the universe exists in a context of forces that are indifferent to whether it continues or ends, maintained by conditions that are specific enough to be remarkable and temporary enough to be temporary. The nuclear pasta in a neutron star is the hardest thing that exists, and it exists inside a dead star, the remnant of something that spent millions of years in a state of dynamic balance before collapsing into the most compressed form of matter. Physics permits while still occupying space. The magnetar's field is the strongest thing that exists, and it is slowly decaying, losing rotational energy, weakening over millions of years, eventually becoming a quiet neutron star indistinguishable from any other. The extraordinary phase of its existence, just a chapter in a longer cooling curve. The spaghettification events happening right now in galaxies across the observable universe are the endings of stars that had spent billions of years in stable orbits before drifting close enough to a black hole's tidal radius for the gradient to become catastrophic. Stability ending not through any change in the rules, but through the slow accumulation of orbital dynamics that eventually placed an ordinary star in an extraordinary position. The black hole and white hole, paired in the same equation, are the same object at different points in a timeline so long that the entire current age of the universe might not be enough to see the transition complete. And yet the transition is built into the mathematics from the beginning. The full cycle encoded in the equations from the first moment of collapse. The order we live inside is the most improbable thing in the observable universe. and it is the thing we are most likely to take for granted, precisely because it has been stable long enough for us to mistake duration for permanence. The universe does not deal in permanence. It deals in processes, in the long, patient operation of forces that build structures from uniformity, sustain them through balance, and eventually dismantle them back into the components that will form the next iteration of something we haven't yet imagined. We are inside one of those structures, during one of those sustained balances, at a moment early enough in the universe's history that the processes of dissolution are still distant and the conditions for complexity are still operating, but late enough that the extreme endpoints of those same processes are already observable, already catalogued, already named after pasta, and given precise measurements in units of Gauss and solar masses and light years. The fact that we can name them nuclear pasta, Magnetar, Spaghettification, tidal disruption event, Oort cloud perturbation means we have crossed the threshold between being subject to these forces in ignorance and being subject to them with understanding, which changes the experience even when it cannot change the physics. Consider what that threshold represents. For almost the entire history of the universe, for the first 13.8 billion years, there were no observers capable of understanding what was happening at the level described tonight. Stars lived and died, and compressed into neutron stars, and the nuclear pasta inside them formed and deformed under pressures no laboratory can produce. And all of it happened without any structure in the universe sophisticated enough to ask why, or to measure it, or to give it a name borrowed from Italian food. The emergence of observers, structures complex enough to model the universe they're embedded in, to detect gravitational waves from neutron star mergers, to map 15 million galaxies and notice that dark energy might be weakening, to calculate that a dim orange star 62 light-years away will disturb the outer edges of the solar system in 1.29 million years, is itself one of the most extraordinary things that has happened in the universe. And it happened inside the same stability window we've been describing all night, the stable Goldilocks period, the quiet interlude between galactic mergers, the protected corner of an unremarkable galaxy where a medium-sized star happened to have a rocky planet in the right orbital band. This is the context in which the universe produced the first structures capable of understanding any of what tonight described, which means that the fragility of the order we live inside and the capacity to appreciate that fragility are connected. One made the other possible, and the appreciation is meaningful in direct proportion to the understanding that the conditions producing it are temporary. Every structure, every stable arrangement of matter in the universe exists in a context of forces that are indifferent to whether it continues or ends, maintained by conditions that are specific enough to be remarkable and temporary enough to eventually end. The nuclear pasta in a neutron star is the hardest thing that exists, and it exists inside a dead star, the remnant of something that spent millions of years in a state of dynamic balance before collapsing into the most compressed form of matter physics permits, while still occupying space. The magnetar's field is the strongest thing that exists, and it is slowly decaying, losing rotational energy, weakening over millions of years, eventually becoming a quiet neutron star, indistinguishable from any other, the extraordinary phase of its existence, just a chapter in a longer cooling curve. The spaghettification events happening right now in galaxies across the observable universe are the endings of stars that had spent billions of years in stable orbits before drifting close enough to a black hole's tidal radius for the problem's gradient to become catastrophic. Stability ending, not through any change in the rules, but through the slow accumulation of orbital dynamics that eventually placed an ordinary star in an extraordinary position. The order we live inside is the most improbable thing in the observable universe, and it is the thing we are most likely to take for granted, precisely because it has been stable long enough for us to mistake duration for permanence. The universe does not deal in permanence. It deals in processes, in the long, patient operation of forces that build structures from uniformity, sustain them through balance, and eventually dismantle them back into the components that will form the next iteration of something we haven't yet imagined. Understanding doesn't change the physics, but it changes what the physics means to the structures inside it that are capable of understanding. And that capacity for orientation, for situating yourself within a universe that operates at scales and timescales your intuition was never designed to process, is the thing that tonight was really about. The gravity holding you in place right now is the same force that, somewhere across the observable universe, is currently stretching a star into a spiral of plasma 400 million kilometers long and feeding it into an object from which nothing escapes. The same inverse square law, the same mathematics, the same fundamental relationship between mass and curvature, running at a scale and intensity that produces something categorically unrecognizable from the comfortable physics of falling objects and orbital periods. And somewhere in the balance between what builds and what destroys, between the order that persists for billions of years and the forces that eventually end it, is where every structure that has ever existed finds itself. For however long the conditions hold, order holds the way a flame holds continuously, dynamically, sustained by the ongoing interaction of forces that could end it at any moment and haven't yet, meaningful in direct proportion to how clearly you understand what it takes to keep it burning, and beautiful in exactly the proportion that its impermanence is real